Okay, dear student, let us see what is there in this question. The centers of two identical fixed conducting spheres, each of charge plus q. So this is plus q, and this is also plus q. They are separated by a distance capital D. C is the midpoint of the line joining the centers of the sphere. Sketch on the axis how the electric potential V due to the two charges varies with the distance r, small r, from the center of the left charge. Okay, that is x is equal to 0. No numbers are required. Your graph should extend from r is equal to 0 to r is equal to capital D. Okay, so this is the graph in front of you, and it wants you to comment on the potential. Okay, so what is happening? We have to be very careful here. Like at this point, this is like r is equal to the small r is equal to the radius, or you can say capital R, but it is not given, so we can just assume it to be capital R. And we have to be careful for this region also. And this is x is equal to D. This is x is equal to D. So we want to make a graph from x is equal to 0 to x is equal to D. And the graph will be about the potential. So, point to be noted here is that the potential is given by a formula that is the potential is given by K capital Q divided by R, where capital Q is the charge of that particle, like which is the source charge, and R, small r, is the distance at which you are trying to find the potential. So this potential is given by this. Now what happens is, let us discuss about the point C, and let us try to find like what will be the potential at point C, and that will clarify each and everything. So this charge is capital Q, and from this point, from the center of the charge, we would be measuring the distance. That will be clearly d by 2, isn't it? So at this distance r, like we can just assume it to be small r, like small r is a random value, so it could have any value, it's a variable. Let us say it is small r. So the potential will be given by kq by r. So we will first find the potential due to the first sphere. Let us call this first sphere. I'm just naming it, but it's not like first or second, but just name it. The concept is positive charge will cast positive potential everywhere, like around itself. You would be finding positive potential if you're referring to the positive charge. So this is positive charge, so there is a positive potential that is created by the first sphere. The second sphere is also positive charge, so even that is casting positive potential everywhere. So even this is going to create a positive potential at this point. Now, potential is a scalar quantity, although it can have two values, like either positive or negative. Negative charge will be creating negative potential. Positive charge will create positive potential. In this case, both of charges are positive, so V1 and V2 are positive. Now, because it is a scalar quantity, we were just going to add it in a simple algebraic manner, so that will be V1 plus V2. So this will become some potential here. But as you start reducing, like some, it will be added here, and you would be having a positive value, let us say. So this is definitely not zero, but it is a positive value here, something. The another concept that you need to understand is, like, as the distance reduces from one sphere, as the distance reduces, the value of potential will increase. If the value of potential will increase, so this potential V1 is increasing, but V2 is reducing. But the reduction will not be that big, but the increment will be very high. Okay, so increment will be exponential. So that is why, if I'm going to talk about this point, so V1 is going to increase multitude times, but V2 will be decreasing, but it will not be decreasing that much. So I can say that here the potential is at this point, and same symmetry will be there, because there is a symmetry in the question, like charges are equal, they are equally spaced and everything. It's completely uniform, both are positive charges. So this will be the V, and this will also be V, and in between there will be kinda this kinda we can say, kind of variation. Now, what about inside of a sphere? So this is the potential, like let us say this is the graph. So this is the potential at the surface of this, and this is the potential at the surface of the second sphere. Now, inside of a metallic sphere, like when you go into it, there is another thing that you need to understand. This is a concept. The potential inside a conductor is always equal to the potential which is at the surface of the conductor. So it is not going to increase. It means that the potential due to like whichsoever surface, whatever is the potential here, that potential is going to remain constant now. So this will become like this. So whatever is the potential on the surface, that is going to become constant because there is no electric field inside of a conductor. And there is a, like, it's a big concept. E is equal to negative dv by dr is the formula that relates electric field and the potential. So electric field inside a conductor is always zero, whether the electric field is created by somebody else, some other charge, or it is being created by the charge itself, whatever. The electric field inside a conductor is zero, and that can happen only if the potential difference is zero. So there will be no potential difference here. Similarly, this is going to be a constant value here. So even this is going to be a horizontal line because the potential inside a conductor is always equal to the potential at the surface. Solid sphere, it's in the case of no, sorry, not the solid sphere. This is the case of shell, basically. But electric field on the two charges vary. Yeah, but they are talking about the charges only. So the radius is not given. Yeah, so we can just assume it to be this. A bit confusion is here because the radius of the sphere is not given. But anyways, so this will be um horizontal. There is no other option. So this is what is going to happen, and the potential will be this. Like, if I assume that this is not a sphere but this is actually a charge, let us say this is a charge. So the radius is the radius is negligible, let us say. So when this r will become zero, the potential will become infinite. So your answer should be at this surface, it should be in an asymptote should be there. It should go like this, and it should go like this. So there will be some asymptotes, but that is not the case in this because I think they will be taking it as a sphere, and we will see it in the answers also. Okay, so this is how we do the first question. Let us see what is the answer that they have given. And yes, they are talking in the same manner. Constant non-zero within the spheres. So it is a constant value but non-zero value within the sphere. A clear non-zero positive value minimum at C. So C's value is positive, but it is minimum, as we have already told you. Symmetric bowl shape up curved between. So this will be a symmetric bowl. So the symmetry of like this is basically the mirror image of the other. So there is a complete symmetry there. Anyways, so this is the answer for the first question. Let us go for the second one. Calculate the work done to bring a charge Q from infinity to the point C. Now, how are we going to do this? So we are going to use the formula that work done is equal to the product of charge and the potential difference between two positions in which a charge small q is moved. So we have to find the potential at two positions. Number one, infinity, and number two, C, because the charge is moved from infinity to point C. So obviously the potential at infinity is always taken to be zero, whatever it is, like there are two spheres or three spheres, doesn't matter. So the potential at infinity is zero, but the potential at C is not zero, as we have already seen in our graph. So we will first find the value of V1, then we will find V2, and then we will add it. So V1 will be K Q divided by R, which will be half of this, kinda 0.6 meters. Q value capital will be taken, not the small q. Okay, capital Q. The source charge is important here. This is the potential because of the first charge. Now the potential because of the second is also going to be exactly same. So V1 is equal to V2, and now we are going to add them. So our total potential is V1 plus V2, which becomes KQ divided by zero point 0.3, because it is actually multiplied by 2 now, because there are two potentials like V1 and V2, so they are just getting. So this is the net potential at C, isn't it? And the potential at in this is 0. So what is delta V? So now we would be talking in the terms of like final minus initial. So final is VC, initial is 0, which is at infinity. That will be work done. So from by using that formula, W is equal to Q into VC which is this, into capital Q divided by R. So we have just substituted our values here, and now we can solve this. So this and this gets cancelled out, and this decimal can be removed by multiplying 10 in the numerator. So this will be 3. So 4 3s are 12, 12 2s are 24. So 24 into 10 is per negative 2, so 0.24 joule. This is the net work done in bringing a charge from infinity to that point. Now the answer will be 0.24. That's it. And let us now move next. So let us see what is the answer. 0.24, clearly the answer that we get is absolutely correct. And let us go for the next part, which is 6b1. Okay, so the small positive charge q is placed at a distance x from the center of C. This is a positive charge q, this is also a positive charge q. But this is a small charge q, but it is also positive. Now this is placed at a distance x away from the charge C, from the point C. The distance x is very small when it compares to capital D. The magnitude of the net force on the charge q is given by this. So this is the net force. So let us see, F is equal to 32k capital Q small q capital D cube into x. This is the force, that is the net force which is acting, and only the magnitude is given. They are still not talking about the direction, but we will make it. Explain why the charge q will execute simple harmonic motion about C. So whenever you get a question like this, like why it is going to be a simple harmonic, the answer is again like always the same. What is that? This F has to be replaced with F is equal to m into A. So mass of the charge, let us say this mass is m. So this mass goes to the other side. So we can say acceleration is equal to x. So acceleration is directly proportional to x. And which direction will it be? Because it has to be negative x, otherwise it is not a simple harmonic motion. So we have to prove it that the direction is towards the mean position. Now obviously this charge is also casting a repulsive force here. It would be creating repulsive force here, but this charge is also creating a repulsive force, but this force will be greater in blue, and it will be greater than the other force. Why? Because the distance from the second charge is lesser, but the distance from the first charge is bigger, so that force will be lesser. So there is a net force which is in the right hand side direction, which is towards the mean position. So definitely there is a negative sign also which is involved here. So we can say that this is the necessary and sufficient condition to prove that the motion will be a simple harmonic motion. So that's it. So this condition is fulfilled, and we can clearly say that yes, this charge will be executing simple harmonic motion. Okay, let us now move to next thing, and I would be showing you the answer later. So the mass of the charge is given now. Calculate the angular frequency from this and this, and the mass is also given. So angular frequency, so we created these this thing earlier, so I'm going to continue from this position only now. So how to move now? So we know that the fundamental equation of simple harmonic motion is given by acceleration is equal to negative of omega square x. See, my dear students, whenever it is about the simple harmonic motion, you are going to get a repeat telecast of this question. again and again. Nothing new about it. The only formula is A is equal to negative omega square x. You just need to follow the pattern. Follow the pattern that I am using here, and it will be good to go with. There was another question I remember doing it, like f is given as rho g a x. There was a negative sign. This kind of a question was also there, and in that also you wanted to find the angular frequency, and later you want to find the time period. So you would be following the same pattern in these kind of questions. So this is the pattern that you have to remember. First of all, we will create this expression for acceleration, and then this is the fundamental equation. We are now going to compare it. So omega square will be equal to 32k capital Q small q d cube m. This is equal to omega square, and because you want to find the angular frequency, you have to take the square root. So this is your answer. This becomes the omega, the angular frequency. If you want, like, there are two relations you have to remember. It is like 2 pi divided by t if you want to find the time period, and 1 by t is the frequency f, which is in the hertz. So if you know the omega, you can find the time period for the oscillation, and also you can find the frequency of the motion of the charged particle. Accordingly, you can find, like, whether you what are they asking you in the question, whether they're asking capital T or the f. So this is what you have to do. So this is the omega, time period, and frequency. Let us see what is the answer given. Calculate the angular frequency. Okay, so we will not be calculating. I will be showing you the marking scheme now. Clearly, they have done the same thing. You see, omega is equal to 32k q divided by md cube square root, and I told you to do the same thing. So omega is there, and what else were you supposed to find? Just a moment. Calculate the angular frequency and the expression, in B1. Expression using the data in A2 and the expression in B1. Okay, so basically you want to find the angular frequency, so that we have already done. This is omega 32k capital Q small q divided by md cube. This is what you were supposed to do, and this is the answer that you should be getting, 7.3. So you people can just take your calculators, and you can do the calculation that I had just written here, isn't it? Like this. Okay, let us now move next. Yes, the charges capital Q are replaced by the neutral masses capital M, and the charge small m is replaced by a neutral mass M. So this is capital M, this is also capital M, and they are neutral. There is no electrostatic force, and there is this mass which is small m. It is displaced from the point C, so it is taken to the new position now by the distance x and released. Discuss whether the motion of m will be same as that of the charge q or not. So let us see, like, they are asking whether this will be making the simple harmonic motion this time also or not. Let us see. So if you take this as the uh, position C, yeah, like this. So this point will be there. So when the mass is here, so we can clearly see that this mass will be applying a force of attraction to this, and that will be bigger because the distance is lesser. Well, this capital M will also be applying an attractive force on the small m, but that will be lesser in magnitude because the distance is bigger. It means that the net force on the mass small m is towards the right hand side, which is away from the mean position, which only means that this is not going to be simple harmonic motion. The only thing is this m is experiencing a mass towards capital M, and someday this mass will go and it will fall onto the surface of the that planet or something. So this is going to happen, but it will not be simple harmonic motion. So your answer is this, that it is not going to be the same as that of the small q. Let us see what is the answer given. Yes, the net force will no longer be restoring and directed towards the equilibrium position, and that is why no motion, it will no longer be simple harmonic motion. Yeah, the motion will not be the same. Okay, dear students, so I think this is the last part. Yes, this is the last part for this question, and this is how we do this question. And so, if there is any other doubt, you can also mention that in the comment section. Please share the video with all your friends. Tell them to join the YouTube channel. And thanks for joining this YouTube channel. And I would be uploading more questions now. Okay, then, this is it. All the best.